Okay, the next big topic is connecting what we just did with antiderivatives to area under the curve. Now, I know that might not sound intuitive, and well, I don't really think it should. And it's going to take a little bit to get there. So, what we're going to do is spend the next couple sections finding the area under the curve. Okay, and then somehow we're going to connect the area under the curve to an antiderivative. All right, so at some point, you know what this means, right? This means antiderivative of this function. This is the function shown. And then I still promised you something about limits, so I'm going to have to make the connection to somehow having a limit of something. I'll just kind of leave that blank for now. It's going to be a sum, which is a big jump, but let's just say ... Okay, so three big things we're going to connect in the next few sections. It's going to be area, antiderivative, and limits of something, okay? But first, we're going to start off nice and basic. The basics are to find the area under the curve. Now, we're not going to be able to do this for a little while until we figure out how it all works and connects. So we're just going to do something easy. We're going to estimate. Okay, so let's say this is like before we get to the calculus part. So there's no calculus involved in the answer to the following question. How would you estimate the area under the curve from 0 to 2 under that function? Well, if I wanted to show you the exact area, I would say, okay, how do we do this? Let's label it first. This is quite a complicated question, right? It's this area. The exact area. How are we going to do that? It's actually a fascinating result. I'll get there in a couple lessons. It's really, really interesting, I think, how we can find this exact area. Because look at this. The only area you've ever really calculated before probably is like rectangles and circles and things you have nice geometric formulas for, squares, right? But this is just a funky shape. I don't know anything that's a geometric shape that this is like under a quadratic curve, right? So we don't know really how to go. So what we're going to do is kind of work the process of how this was really discovered. So we would say, what would the logical step be? I think the logical step would be to estimate it. Okay, so what if I change the question? Estimate the area under the curve. Well, if I want to estimate, I got to do geometric figures that I know the area for, and I think the easy thing would be a rectangle. All right, so I'm going to break this up. Let's break it up into 4 equal subdivisions or intervals for x. And I'm going to start at this first one. I'm going to go to the right. This will be called a right endpoint. Go up, hit my graph, and go over. That's a rectangle. I think I could find the area of that. How about this one? Go to the right, go over. There's a rectangle. I can find the area for that. That hits there. Oh, don't know how I did that. There's a rectangle, and there's a rectangle. Okay, think about it. Can you find the area of these 4 rectangles? Well, you should be able to, because you know the formula is length times width, right? So I just have to add 4 of them up. So let's do that. The width, here's the good news. What's the width of each of these? Well, I went from 0 to 2, and I divided them up into 4. So that's the width. So let's see. Let me use this notation. The width of my interval is the big N minus the small n divided by how many rectangles I'm using, which is 4. So I got a little formula for that, which might come in handy later. So the width of each one's a half. What's the height of each rectangle? Well, the height of the first rectangle is the distance from here to the curve. What's the height of the curve? That would be the input of this x value here, which is a half, right? Times the width, which is a half. Plus, how about this rectangle? Well, I'd have to plug in this value. What's that? That's 1. This is a half. This is 1. This is 1 1/2 or 3/2. Right? So does everybody see what I'm doing here? Does this make sense? The height is given by the function value. The width is given by, well, that's constant. They're all 1/2. This height of this rectangle is 3/2. This is pretty messy, right? And the height of this rectangle is 2. So, unfortunately, I'm going to try to keep your homework light because these problems take a lot of time. Okay, so if you look at your homework for 5.1, there shouldn't be too many of these, but you're going to need your calculator handy, right? Because what do? Well, if I want to, before I dive into my calculator, and this is a fairly straightforward one, they do get a bit more complicated. Think trig functions or root functions. I can factor out the 1/2, and then I have each function value added together, summed up. All right, so let's do this one. F of 1/2. So I plug in 1/2. F of 1/2 is negative 1/2 squared. Be careful, you got to square it first and then make it negative. So it's going to be negative 1/4 plus 5. That's my first one. Ugh, don't like that. This one's better. Plug in a 1. 1 squared is 1. Negative 1 plus 5 is 4. 3/2, this one's going to be a little messy. Let's do the work. 3/2 squared is 9/4. And that's negative plus 5. And then f of 2 should be easy since that's an integer. Plug in 2. Here I get 4. Make it negative. Negative 4 plus 5 is 1. Okay, moving right along. Maybe go to my calculator at this point, but I can still do this without a calculator because 5 as a fraction over 4 is 20/4. 4 plus 1 is 5. Let's see, this would be 19/4 plus 11/4. Definitely way more work than we need to do by hand, but I'm already almost there, so I'm going to finish her up. Make sure I did that right. 11/4, 19/4. I believe that's right. That's 30/4, which will reduce to 15/2 plus 5, which is 10/2. So I got 1/2 times 25/2. And my final answer is 25/4. Ugh, a lot of work with arithmetic there, but let's go back to the main purpose of that problem. It was to estimate the curve, okay? Estimate the area under the curve. So the next question is, how good is our estimate? Well, what are we missing? First of all, is it an overestimate or an underestimate? It's definitely an underestimate. The real area is greater than this, right? It's got to be greater than that because I didn't account for these spaces here. I didn't account for this little space, plus that. And I think I missed a little something there. Okay, so I didn't account for that. So the other option would be to do, so this was called a right estimate, right? Or a right end estimate, right estimate. Because what we do is we started at the right end of the interval. I could do it all over again, start at the left end. So let's do it. I won't do all the arithmetic. Just stay with me for the concept. So look, this would be, so still have the 1/2. This is 1. And then this is 3/2, but I would go up instead of going I should be going low. I should be going left. Let me try that again. I know I was doing something wrong there. Let's do left estimates. That didn't look right. So I'm going to start here, go up, and then go over. I'm going to start here, go up, hit my function, and then go over. These should be rectangles. Start here, go over. Start here, go over. Okay, does that make sense? So this will estimate my area, but it should be an overestimate, right? Because now we're over. So the width of each of these would still be 1/2, but look at the height of this first rectangle, which will give me the area. The width times the height would be the width 1/2 times the height, which is given by f of 0. That's the first one, right? So we're starting at 0 this time instead of last time we started at a half, right? And the process would be the same. So it'd be 1/2. What's this rectangle? Well, the height's given by f of 1/2, the left endpoint. And then it'd be f of 1. And then we never make it to f of 2, right? It'd be the last one would be given by this, which that's 3/2, 1.5. You go up, and that's my last rectangle. That's my fourth rectangle. So that would be f of 3/2. Okay, and I'll save you the pain of calculating these, although I will warn you, you're going to have to do a bunch of these for homework. Not a bunch. I tried to reduce it. I don't want to make you do too many of these because it's just a lot of arithmetic work. Okay, so this would be a right estimate and an underestimate, because the real area should be more than that. This would be a left estimate since we started at the left, and it ends up being an over. That's not always the case. Depends on really if what the function does. But this would be a left estimate, and it would be an overestimate, right? The area would be greater than the actual area. And then the third option, which wouldn't really work that well for this one, but you can do it, would be a midpoint guy. So I'd find all these midpoints. That would be, this isn't the best example for a midpoint. It's a good example for left and right, but this you could do, this would be 1/4. And then if you add 1 to that, that would be 1 1/4. I'm sorry, if you add 1/2 to that, since that's the width, same width. It wouldn't make sense too much for this one. But you get the idea, because if I go up, well, I guess it could make sense. And you hit, and it's a better estimate, right? Because you don't go over or under as much. So I'm right in the middle of each of these. So there's one rectangle. This is the midpoint method. All right, here's your next guy. All right, and you get the height of these by plugging in these midpoints. So this would be 1/4 plus 1/2, which is 2/4. So that's 3/4. And then I do it again. If I had 2/4, that would be 5/4. All right, to get to this next one. Sorry, these rectangles are not very good. Okay, and you can see how that one works. All right, and then the last one, I guess, would be 7/4. And that's the height of my rectangle is now given by the midpoint instead of the right or the endpoint. So it would be f of 1/4, f of 3/4, f of 5/4, f of 7/4, and it's still 1/2 times each of those. And then we add them up. Okay, and that's probably the best estimate. All right, so that is estimating area under the curve. Now, eventually, what I want to do is find the exact area under the curve. So let me take just 2 minutes and show you where we're going with this. Okay, so this is where we're going. Let me show you. Well, let's see if I can get this a little bit bigger. Hang on. Okay, so this is where we're going. So this I could ask you to do this problem and say the function is x squared. Well, let's see. Let's see if we can get our. They let me go. What was mine? Negative x squared plus 5. Okay, good. And I want to just, I'm only interested, upper bound is 2. Nope. There we go. Okay, and we did n was 4. Okay, that should look familiar. That was the first example I did. Okay, and that was lower rectangles. And let's say, what if I said right endpoints, right? Same thing. We said the lower endpoints was the right end, the lower rectangles or the lower estimate were right endpoints. And then the other one was we did the upper, which just happened to be the same as the left endpoints. Okay. Now, here is the concept, which this is the direction we're going. What we want is the exact area under the curve. So what could you do to make your estimate better? Well, I could have more rectangles, right? What if I had 12? Well, that's pretty good. I'm still an overestimate with the left. Of course, that'd be an underestimate with the right, but the idea is to make a whole bunch of rectangles. Look how good